our work entitled Mini but Mighty Fine-Tuning ViTs with Mini Adapters. This work has been done at LTC Lab in Telecom Paris by me and my two supervisors Enzo Tartaglione and Stéphane Lathuilière. The objective of this work is how can we fine-tune large visual models using only few parameters. As you might already know, Vision Transformers has achieved state-of-the-art results on many different tasks such as image classification, semantic segmentation, object detection, and many more. But the main issue about using Vision Transformers on downstream tasks is that they require a lot of training cost due to the fact that they have a large number of trainable parameters. So there has been many works known as parameter efficient training methods in order to fine-tune and achieve really good performance on downstream tasks using only few number of trainable parameters such as adapters, visual prompts, and comparators, and many more works. In our work, we will focus mainly on adapters, which are small blocks injected into each layer of the VIT backbone, as illustrated here in the figure. And during the fine-tuning stage, you will only fine-tune the parameters of the adapters. But the main issue with this approach is that it introduces high inference cost, and also it requires a lot of storage memory due to the fact that for each downstream task you need to store a high number of trainable parameters. And also we have noticed that the performance you gain at the fine-tuning stage on the downstream task is subject to the number of trainable parameters you inject. So if you have large size for your adapters, the performance will be really good. If the size is really small, the performance is really bad. So the objective was how can we have smaller adapters but we still maintain really high performance. And therefore we introduce our Mimi, where basically it is a fine-tuning method based on adapters that employs dynamic adaptation for the adapter size, where we keep adapters at some layers if it is necessary for the downstream task. If it's not, then we will remove them in order to reduce the inference overhead and also the memory storage cost. The algorithm of our approach here is illustrated in algorithm 1, where we basically start with over-parameterized adapters, and then during the fine-tuning stage, we rank the neurons for each adapters in all the layers, and then we discard the neurons that have low importance scores according to the introduced importance score, where basically it takes in consideration the magnitude of each neuron in the downsampling and upsampling layer in the adapters. If it's really high, it means that this neuron is really important to the downstream task. If it's not, then we will discard them and keep fine-tuning only the most important neurons. Here in figure 1, we illustrate the main difference between our approach and adapters and full fine-tuning, where we can see that for adapters approach them where the size of adapters is really small, the performance is really bad, as you can see here. On the other hand, using our approach Mimi, we still maintain really good performance even though the size of adapters is getting smaller and smaller. Or furthermore, the most important aspect of our approach is that it dynamically adjusts the size of adapters according to downstream tasks. So here in figure 3, we show the remaining neurons in each layer in the adapters on VGG flowers and C500, where we can see that for the early layers for VGG, when we find on VGG flowers, that the neurons has been removed completely, which means that the early layers representations from the pre-trained VIT backbone are already good enough for this downstream task, so we don't need any adapter in order to adjust this representation. On the other hand, for CFR 100, where we can see that the adapters are still maintained, but with a smaller number of neurons, which means that almost all the layers in the VIT backbone need some adaptation for the downstream task. Furthermore, in our main paper, we show that our approach does generalize to various VIT bipoles such as swing VIT and CVT, and always outperforms adapters, although using a small number of trainable parameters. The code and the full paper are available at our website. You can check that by scanning the QR code. If you have any questions, do not hesitate to send email or open an issue at the GitHub repo. Thank you.